Welcome folks. So this is again continuing our video series on PMSM field-oriented control. And so last time we looked at how to create this steady state PMSM model, and we created the two different models. We looked at the differences and the similarities of the two. So I hope all of you had the opportunity to try it yourself. And so today we're going to use this PMSM model, the steady state model, and we will try to implement field-oriented control. So this is the simplest form of field-oriented control that you're going to see that uses this rotor reference frame. And the goal here is that to implement two PI controllers for each axis, because our zero axis or zero sequence is assumed to be zero at this in this discussion. And now treating these two axes as independent DC motor equations, so they look like DC at this point. We're going to be implementing two PI controllers and trying to implement this in Simulink and then see if that works. Okay, I have a longer video that explains the design process, so feel free to check that out in the other playlist. But this is the basic overview or the block diagram that you're going to see. We have our PMSM model. Since we are looking at a torque controlled system, our speed is maintained by the dynamometer or the interaction of the torque and the load torque, electromagnetic torque from the motor and the load torque. So that that sets the frequency, that sets the motor speed, and we only have to set up the PI controllers, obtain the Q and D currents, and then pass them through the PI regulators. If you design them properly, you're going to get the desired response from the two. Now, since we are not looking at stationary frame, our currents are going to be DC-like. But if you do need to look at the stator reference frame currents, I'll show you how to find those in the model. Okay, and in designing our PI controllers, we are following this very simple approach. Basically, your Kp is bandwidth times inductance, your Ki is bandwidth times resistance. Now in this case, since I'm considering a surface mount magnet PMSM, our Q and D axis inductances are the same. Hence, both the Kp and the Ki values for Q and D axis is going to be the same. If you have different inductances for Q and D axis, you can modify your PI controllers to be different if you need to do that. Okay, but typically this approach works fine. And for folks who don't have an idea of what this bandwidth variable does, is it actually helps you set up the frequency response of the closed loop system. Simply speaking, if you are considering a first order system, bandwidth or the cutoff is considered as this negative 3 dB frequency, right? So by designing our controller in this fashion, we are trying to achieve such a response in our PMSM system. Okay, so this is basically an overview of what this is going to look like. So let's jump into our Simulink model here. All right, so here this is basically very similar to what you saw in the diagram we drew, right? We have one of our steady state models that we built last time, and then I'm taking those currents and feeding them back. I have a step input here for Q axis current reference. ID reference is set to 0, and I've defined my Kp and Ki values in a script here. So I'm going to pull that up. So these are the same parameters that we saw last time, and then I'm calculating my Kp and Ki using this bandwidth and then LQ and resistance. So that's done. And so that's all actually we have to do. We don't need the position signal as of yet, because we don't have a stationary frame signal. We don't have a sinusoidal signal yet. You're going to see that in the future. We do need the speed information, and we are providing that speed information from one of these go to and from labels, and that makes your model quite a bit less cluttered. This looks very professional when you do that, so that's why I'm using those labels. And then I'm using these IQ and ID values along with the position signal to see what the ABC currents would look like, or the stationary frame currents would look like, and then transforming them back into the DQ frame just to see if they work. Okay, so you can try this yourself and see if it works. Now be careful when you implement these. Don't have plus signs. You're gonna get errors if you do that. And then if you have unexpected loops in your model, you could also get some errors from simulating. So just keep an eye out for that. Try to follow what I have done here. So when I run this model, you can see that it takes a little bit of time because of how we have implemented our steady state PMSM model. So we'll let it run. And in the meantime, what I would like you to do, if you are following this series, think about how you can add dynamics to this model. So the next time we're going to look at what the dynamic PMSM model in Rotor reference frame looks like. So if you're following my lectures, try to implement that yourself, because now we can directly replace this model with the dynamic model and see what that does to our system, right? So that's our next video. Since our model is taking some time to run, I'd like you to try this yourself. So this is going to be a good learning experience for you. Try it, and then you can see if you are getting close to what I'm modeling in my next video. So if you have some time over, try that out. Okay, so we are almost at 70 or 80% mark, so this should be done very soon, and we'll be able to take a look at what the response looks like. Try to open it up. Yeah, so actually you can see it running. All right, so the first is your Q-axis response. So I'm injecting very small current. So initially set your starting current to be about 0.01, and then I'm injecting a step input of 2 amps. The reference is being changed to 2 amps at this t equals 1 second, and we can see that the controller is following that. Okay, and then you can also see here the d-axis response is regulated to be 0, and then during that transient state we have cross coupling, right? Remember, we saw cross coupling between the d and the q axis. Due to that nature, you see some transient. However, since we have a closed loop controller on d axis, that is being suppressed by injecting additional voltage into the q axis of the motor, and that's driven to 0. So now we actually get very nice performance from our system. If you want to avoid this transient on the d-axis, you can implement cross-axis decoupling. So that decoupling helps you mitigate such coupling between the two axes. So that may be for a later video down the road. And here this bottom graph is showing you what the torque looks like. So torque is almost 0 at this level, right? And then you can see your torque proportionally rise to that desired level. Okay, so now by changing this reference, you can now look at different profiles of this steady state motor model. Okay, all right. So, well, our closed loop system is working. Now let's take a look at our ABC currents here. Okay, there we go. So we have very nice, very well behaved. You see currents, we have, if you look at this initial stage, this is your transient, but all the currents are driven to almost zero. Okay, and when we look at this, the second portion where we have the step input of 2 amps, you can see that we have the peak-to-peak value of current being regulated to 2 amps, right? So this is why we use voltage invariant method or current invariant method in our transformations rather than power invariant, because in the voltage invariant method we get this nice relationship, okay, between the rotor reference frame and the stator reference frame. So you can see your ABC currents as well as your DQ currents using this. And again, this is a steady state model behavior with closed loop. Okay, all right. So in our next video, we're going to be looking at the dynamic model for in the rotor reference frame. So like I mentioned, I'd like you to try this, before I post the next video, hopefully, and that way you can see if you're following this material. Okay, all right folks, good luck, and I will see you in a future video. Thank you.